Hey everyone, welcome into this last video of the lecture series on the review of exponentials and logarithmic functions. In this video we'd like to talk a little bit about derivatives and antiderivatives of these functions. So let's start with derivatives. Let's remember the definitions of both of our functions here and recall that they both kind of have derivatives built into them. First of all, let's remember that the natural log of x is defined to be the integral from 1 to x of 1 over t dt. And so the derivative of this, we didn't work this out in the last video, but I hope you remember, this looks a lot like the fundamental theorem of calculus, right? So the derivative of the natural log of x is equal to the derivative with respect to x of this integral, 1 to x, 1 over t dt, and the fundamental theorem of calculus part 1 tells us that this is just 1 over x, okay? So that's 1 over x. Now, so there you go, there's a formula, right? The derivative of natural log of x is equal to 1 over x. Now let's check one more thing here. What if we were to take the natural log of the function minus x? So this is a chain rule, right? Here we have a function u on the inside. U is equal to minus x. The function on the outside is the natural log becomes the natural log of u. So here's a chain rule, right? So this becomes, I'll call it f, is equal to the natural log of u. And then if we take these derivatives with respect to their respective variables, the derivative of natural log u, we just said that should be 1 over u. And the derivative of u with respect to x is just -1, right? And of course the chain rule says that we should multiply these together, right? So the derivative of the natural log of minus x is equal to this product, f prime times u prime. All right, you have to be very careful. This notation is a little misleading, but I think it's common enough that we're okay with it. This then becomes -1 over u, but you have to remember what u is, right? U is another negative x, and then what's going to happen? You're just going to get 1 over x, right? And so notice that we have now two functions, the natural log of x itself and the natural log of minus x, that have the same derivative. It's 1 over x, right? And this then leads us to a formula for an antiderivative. So I'll write this as number 2 in this lecture. The antiderivative of 1 over x dx. Now, we use the fundamental theorem with a definite integral to define the natural log, so it's not a surprise that the indefinite integral, or the antiderivative, would be related to the same function, right? But it's not exactly the natural log, so it turns out it has to be, because of the minus in here, it turns out it has to be the natural log of the absolute value of x plus c. All right, so this is a formula that you should remember, but in case you don't remember it, you have to know that one, right? You have to know that one. This is one, obviously you have to know derivative of natural log is 1 over x. All right, here's another example. What if I want to find the antiderivative of x over 3 plus 2x squared dx? So how would I do this, right? Well, based on what we've done before, this looks kind of like this, but not really. It's just not, it's not clear, right? So what we want to do on this one is we want to take a u substitution, or make, I should say, a u substitution, similar to what we did up here, but for integrals instead of for the chain rule. And we're going to set our u equal to 3 plus 2x squared. All right? Whenever you make a u substitution, you choose your u, you are not allowed to choose du. You have to compute it, right? You have to compute your du. The du is always the derivative of u, so it's u prime times dx. And in this case, it's going to be what? 4x dx. And then you look back at your equation and you ask, do I have everything I need? So I'll highlight this in blue because this is blue. I know red doesn't go with yellow, but we've got our dx, we've got our x. That's this, right? What about the 4? Well, we can put the 4 there, right? We can put the 4 there as long as we, in turn, divide it out here. So you can multiply by 4 on the inside, divide by 4 on the outside, and you have then not changed anything. And if we go back to our highlighter, that's got to be included in our du, right? So that whole thing just becomes du, and everything from down here is just u. All right, we're ready to rewrite this now, right? So this then becomes, our integral becomes 1/4, that's new, integral of du over u. This is the same, though, as 1/4 integral of 1 over u du. And looking at our formula here, we know exactly what the answer is to that one, right? This is 1/4 natural log of absolute value of u plus c, always plus c. And so the antiderivative, we have to plug back in what our u is, right? The antiderivative is then 1/4 natural log of the absolute value, 3 plus 2x squared plus c. This 3 plus 2x squared is always positive, so if you drop these bars, it's okay. But sometimes it's not okay, right? If the function inside of your natural log could be negative, then you cannot drop those bars. So I would say just err on the side of caution and always keep those bars there. So there we go. So by the way, we do not yet know, and we will learn this very soon, but we do not yet know how to compute this, the antiderivative of the natural log itself. You could do some guessing and checking, and maybe you would get lucky and come up with it, but we don't know this yet. We haven't learned this yet. Okay, so there is some review of our natural log. Let's say one more thing though. So you guys might remember, so I'll call this item number 5. You guys might remember the change of base formulas. So the change of base formula. The change of base formula says the following. So let's say we have log base a of x, all right, where a, so this is for any a not equal to 1 but bigger than 0, and this a is called the base of our logarithm. It turns out that the log of any base can always be written in terms of the natural log, and the way that it works is you write this as the natural log of x, right, divided by the natural log of that base. So this is the change of base formula. You really have to know this one. But what it allows us to do is take derivatives of logs of any base. And by the way, in different areas of math and science, log base 10 and log base 2 are very common. You'll see those all the time. So you will have to do this. This is going to be necessary for you. So let's do that, right? Let's try to find the derivative with respect to x of the function log base 2 of x. Well, according to our change of base, this is the derivative with respect to x of the natural log of x divided by the natural log of 2. And we might not like this number too much. It might not look, nice to us right now. It will someday. But this is just a number, and derivatives are linear. So you can factor that out and then just take the derivative of the natural log of x. And this one is the one we know the formula of, right? So this then becomes 1 over natural log 2 times 1 over x. Or you could rewrite all of this as 1 over x times the natural log of 2. And hopefully at this point you see we have a general formula, right? So this, just by replacing the 2 with a generic a, you will see that the derivative of log base a of x is always 1 over x times the natural log of that base. All right, so let's do one more example here. Excuse me. Let's take the derivative of log, nothing written, but log, of x squared minus 3x. All right, this is going to be a chain rule, and I hope you remember that whenever the log's base is not shown, it's actually not e. It's e if you write ln for natural log, but if you don't write anything and just write log, then it's base 10. So based on our formula, we don't need to go through all this shenanigans every single time. We just need to recognize the formula, right? So this is going to be, we have a couple things to take care of here though. It's going to be a chain rule, right? So it's going to be u. So this is going to be u prime by the chain rule over u by the, derivative of this, times the natural log of 10, natural log of the base. And then we just have to be careful about what u prime and u are. So u prime is the derivative of the inside. So this is 2x minus 3, divided by u, which I'll put in parentheses, x squared minus 3x, all times natural log of 10. That's all on the bottom. All right, so there you go. There's some good examples of derivatives and antiderivatives using the natural log. Let's go back and talk about our exponential function, right? So I'm sure you remember, what number am I on? I'm up to 6. So for number 6, one of the many definitions that we gave of the natural exponential function is that it is the non-zero function whose derivative is equal to itself, right? So this leads us to another obvious kind of formula here. This is really nice, by the way, right? It's easy to remember. This leads us to another nice formula, though, and that is that the antiderivative of e to the x is essentially equal to itself, but actually it's not, right? Because what do you have to do? Whenever you take an antiderivative, you always add a constant. So the antiderivative of e to the x dx is equal to e to the x plus c, always plus c. All right, let's do one example here before we talk about different bases, because you can change the base of an exponential function as well. And let's do this one. Let's try to take the integral of x e to the 4x squared plus 1, all upstairs, dx. So this is obviously going to be yet another u sub, right? Let me get my highlighter back out. Let's highlight this one with red. So that's going to be our u, right? That's the innermost function. So let's write this down then. We're going to put our u equal to 4x squared plus 1, and then automatically compute your du. You do not get to choose your du. Take the derivative. This is 8x dx, and then you ask, do you have what you need? Well, I've got an x dx, x dx. I don't have the 8, right? So I have to put it back in there. So I can put 8 here as long as I take away 8 from here. And then you're good to go. And at this point, what does this become? It becomes 1/8 integral e to the u du, antiderivative, right? And we know the answer. The answer is 1/8 e to the u plus c. And now we just plug back in what u is. So this is 1/8 e to the 4x squared plus 1, all upstairs, plus c. All right, so let's try to take the derivative and the integral, or at least find formulas for these when the base is not e. And for this, we need to recall the relationship between the natural log and the exponential function. So recall that, what? There's a couple things here. The natural log of e to the x is always equal to x. This is always true, right? So this is true for all x. All right, and on the other hand, e to the ln of x is equal to x whenever, what's the domain of log? X has to be greater than 0, right? So if x is greater than 0, then if you can exponentiate this and get back your x. All right, now we can use these properties. So let's suppose, this is our goal. Let's suppose that we want to compute the derivative, d by dx, of 10 to the power x. Again, a function that you might see in applications because our counting system, our number system, is base 10. So you're gonna encounter powers of 10 all the time, and we want to compute this, right? So here's what we can do. Let's recall, just based on which one do we want to look at here? Based on this one, right? So 10 is equal to e to the ln of 10. Do you believe this? Do you believe it? This formula is true for all x that are positive. 10 is positive, so that's got to be true, right? And so what we can do at this point is we can replace, in our parentheses here, we can replace the 10 with this whole thing, right? 10 can be replaced by e to the ln of 10. But it's got to be in parentheses because then there's another exponent. E to the ln of 10 to the power x. But then we can distribute through, right? You raise e to a power, the whole thing to a power. You multiply those powers together, right? So then this just becomes e to the power x times ln of 10. And when we take the derivative, this is a chain rule, right? Derivative of e, so d by dx, of e to the u is u prime e to the u. Should definitely have this memorized. Write it down if not. For this problem, the u is all of this, right? X ln 10, that's a constant times x, even though I've written it in kind of a weird way. Constant times x. And so what we found then is that the derivative of 10 to the x is equal to u prime e to the u. U prime is natural log of 10. E to the u is e to the x ln of 10. But based on everything we just did, right, this is this, right? Kind of funny to write that. It's this, right? It's just 10 again. So this is, well, not all of it, sorry. Let me do it in 2 steps. It's ln of 10 times e to the ln of 10 to the power x, and now these, right? Now that's that. All right, and so this then just becomes natural log of 10 times 10 to the power x. And you might want to put parentheses just to keep it straight. All right, so can we get a general rule then? General rule. Well, of course, for any base, any acceptable base, right, the derivative of a to the power x is just going to be itself times ln of the base, natural log of the base. All right, and it's the same rules have to apply for this base that we've talked about all along. So this is true for a bigger than 0 but not equal to 1. All right. The formula kind of does hold if a is equal to 1, but in general, we don't want a to be equal to 1 when this is a exponential function. All right, let's talk about the integral now. The integral is going to be very similar, right? It's going to be very, very similar. So we're on to number 8 here. So the antiderivative of, I'll just do it in general here, a to the power x dx. We're going to make the same kind of deal here, right? So we are going to write this as, well, number one, I mean, you can see how this is going to be, right? What are you going to have to do? You're going to have to divide through, right? So here's what I'll do. I'll do this in kind of a heuristic sense, but a very important one. So a way that's going to be very useful to us. So we're trying to find a to the x dx, right? And so what I'm going to do is multiply by ln of a. But if I do that, I have to also divide by natural log of a. And now it's very important that a is not 1. All right? And so from here, get my highlighter back out. All of this is an exact differential, or it's a derivative of something, right? And then this thing just has to come out. All right? So this is just going to come out. We've got this here. Let's write out what we have here. So this then becomes, just by a clever observation here, this becomes ln of a times a to the x dx. But all of this can be thought of as 1 over natural log of a, integral of the derivative of a to the x, right? And what do integrals do to derivatives? Well, they cancel them out, right? So this then becomes natural log of a times, oh, it's underneath a 1. It becomes 1 over natural log of a times a to the x plus c. So the antiderivative of a to the x dx is exactly this. All right, let's do one more example, and then we will leave this lecture here. So there's a lot of practice for you in your homework, so please practice it. But let's do one more example. So let's say we want to compute the antiderivative of, well, let's just do something crazy here. Let's say cosine x times pi to the power sine of x plus pi dx. Very, very weird, right? This is weird. All right, so first of all, we need to notice that we have a u sub to compute here. So we're going to try to make this equal to our u and see if it works. So we're going to put our u equal to sine of x plus pi. And then again, we always just compute our du. So the derivative of sine is positive cosine of x. So this is cosine of x dx. And this time, man, I was nice to you. I gave us the exact differential, right? Exact dx. So this whole antiderivative can be rewritten as pi to the power u du. And then we can either go through all that rigmarole, or we can just apply this formula with our a equal to pi. By the way, pi is a positive number that's not equal to 1. So this is perfectly legitimate, right? And our answer is that this becomes, the antiderivative is 1 over the log of pi times pi to the power u plus c. And then we just have to plug back in what u was. So this is 1 over natural log of pi times pi to the power sine of x plus pi plus c. It's a weird one to end on, but it was a good one. So let's leave it there.